Hi, everyone. My name is Bruce Moravchik, and I'm the coordinator of the NOAA Planet Stewards Education Project. And I'm here with Carla McAuliffe, the executive director of the National Earth Science Teachers Association, as well as Dr. Randy Russell. I noted him as an education Imagineer. He is an education instructional designer over at the University Center for Atmospheric Research. And we're looking forward to bringing you our second in a four-part series of elementary school level educational webinars focused on learning and teaching earth science in the classroom. Now, I have a few introductory slides to go through before we turn the mic over to Dr. Russell. So first of all, today's broadcast is being recorded. We're going to be sending you a link to the video archive within a week, hopefully sooner. If you don't receive a link to the archive, please send me an email with the subject, request a link to September 25th webinar. Now, all of the slides and the video archive from today are going to be posted onto the NOAA Planet Stewards Google website. The URL is below. You might want to take a screenshot of this so you remember the URL here. If you have trouble accessing the site, you can send an automated access request through Google, or you can email to me saying that you want access to the site. Be glad to give it to you. We have webinars going back to 2013, some really excellent resources. Now, everyone's microphones will be muted during the broadcast, and if you want to ask a question, please type it into your GoToWebinar control panel. And during the broadcast today, you will be receiving an email from me with a link to a post-webinar poll. Both myself and Carla look at all of the responses that we receive to these polls. They're really very important for understanding the demographics of folks who attend, as well as folks' interest in the webinar. So please go to your email after and respond. We really appreciate it. For those of you who remain on for the entire time, we will be sending you a certificate of attendance signifying that you have received 1.5 contact hours of professional development from the NOAA Planet Stewards Education Project and the National Earth Science Teachers Association. And if you'd like to get another contact hour of professional development, please join our post-webinar online discussion. This will be hosted by two extremely sort of well-experienced educators through NESTA. The link is here, and Carla will be giving more information at the end of the webinar, so stay tuned for that. And also, don't forget, we have 2 more webinars in this series, one tomorrow and one on Thursday. Tomorrow's will be on teaching students about extreme weather and preparedness. That will be done by Mary Fairbanks, a meteorologist in the NOAA's National Weather Service. And we also have Raising the Bar, the Oyster Bar, engaging students with NOAA's 3-dimensional oyster learning sequence. You really don't want to miss this one. This will be done by Bart Merrick, who is the education coordinator for the Chesapeake Bay office from NOAA, our environmental training center, as well as Molly Harrison, who is my compatriot coordinator of the Planet Stewards Project. All of the information is found on the Planet Stewards upcoming events page. And if you enjoy today's webinar, please join us for other activities that we have, such as our book club. We'll be having our next book club meeting on Monday, October 22nd at 8 p.m. Eastern Time. It is free to join and free to participate through the toll-free dial-in number you see in front of you and the passcode. We'll be talking about energy, a human history. But spaces are limited to join in. So please make sure that you are you join early. If you want more information, again, you go to the NOAA Planet Stewards upcoming events page. We have all the books for the book clubs and the dates set out on that page, as well as discussion questions for this book. And we have our next webinar, the Teacher-Friendly Guide to Climate Change, which will be happening on Tuesday, November 13th at 7:30 p.m. It's a terrific resource. We're going to have one of the primary authors, Don Dugan-Haas, who is going to be presenting for us. So I think it's a really excellent opportunity to participate and to find out more about that. Right now, I'm going to open up the microphone for Dr. Russell and introduce him. Again, hi, this is Bruce Moravchik, coordinator of NOAA Planet Stewards Education Project. I'm here with Carla McAuliffe, the executive director of the National Earth Science Teachers Association, and we are pleased to have Randy Russell presenting for us today. Randy works for the K through 12 Science Education Group at a large national research lab, the National Center for Atmospheric Research in Boulder, Colorado. During his 15 years at NCAR, he's developed numerous educational resources for use in earth science education and related STEM fields, with an emphasis on the creation of educational simulations and games. He also leads professional development workshops, both face-to-face and online. Before he joined NCAR, he worked with the Boston-based Turk Group on a series of earth science education interactives, as well as with Michigan State University's Virtual University, developing online courses for science, engineering, and math education. He started off in science and engineering, earning a bachelor's in astrophysics, as well as a master's degree in aerospace engineering. But, like many of us do, he switched gears and earned his doctorate in education from Michigan State. And with that, Dr. Russell, the mic is yours. And now it is yours, Randy. I apologize. You were muted there.
Oh, okay. Thank you, Bruce. Thanks for that introduction. Good afternoon, everybody. And let's get started. Let's see. This is one of my more text-heavy slides, but this will give you a little bit of an idea of what I'm going to try and cover. I'm pretty sure I've got at least 3 hours worth of material, so we won't get to all of it, but we'll do some triage somewhere along the way and hopefully get a glimpse at least most of it. I'll give a little bit more information about myself. Bruce covered most of it in the intro, but just sort of why you might want to think I know anything about modeling. I'll give a little bit of stuff. I felt it was important to do some sort of definitions and theory kind of work, sort of point to the next generation science standards and what they have to say about models and their use in education, and a bit of sort of background, you know, why we're doing this, what I think is important. And then most of the webinar is going to be devoted to examples of things that I think are either informative of what you might do at the elementary level or specific resources that you could potentially use at the elementary level. And running through a bunch of those. We've got some stuff related to tree rings and past climates. We'll talk a bit about glaciers and play around with a simulation of a glacier. A series of things related to ecosystems and sort of more biology related aspects of things. So a game called Food Chain Checkers and some related resources. We'll do a little bit with some molecule models and discuss some things related to modeling around that. I have some stuff around cycles. I'll show you a traveling nitrogen game and describe how you might apply a similar notion to the water cycle, which might be more accessible for elementary students. We'll do a little bit about whether dark or light t-shirts are hotter in the sunshine, and then how that relates to our planet's temperature. And time permitting, we'll try and get to a couple of interactives around the greenhouse effect and a very, very simple climate model. So we'll see how we do on that. Let's see, as Bruce mentioned, I started off in science and engineering, got very interested in education, and have been doing that for 25 or so years now. Um, I've been at the National Center for Atmospheric Research in Boulder for just over 15 years, which is my current location. And I think the rest Bruce sort of covered already. A quick note about the place I work. It's in a beautiful location on a hill in South Boulder in front of our sort of famous Flatirons mountain features right there. I'll probably interchangeably use the term NCAR and UCAR. The National Center is actually NCAR. There's a consortium of universities that have atmospheric science programs that work with the National Center and sort of have oversight for it. We are technically employees of that group, the University Corporation for Atmospheric Research. But as far as you're concerned, they're really essentially interchangeable. I just wanted to clear up confusion because I'll probably reference one at one point and another at another time, treat them as synonyms. I technically work at the UCAR Center for Science Education, or UCAR SciEd for short. One of the reasons that we're particularly interested in modeling and that sort of thing in education is that we run a supercomputing center. So for scientific computing, there's a great big old room. They actually moved the supercomputers out of Boulder a few years back to a site up in Wyoming. So we have a sort of satellite facility up in Cheyenne, Wyoming, and that's where the big supercomputers are these days. And that brings me actually to the first poll question. This is one, oops, I think I just lost my screen and my slides. Let me get back to that. Nope, okay. Just to keep you guys awake and paying attention, this is not one you're necessarily going to have any reason to know the answer for, but might be interesting. Bruce, if you could bring up the poll question about the supercomputers. So this is just, as you probably know, modern supercomputers have a whole bunch of processors in them, a whole bunch of little chips to you know, do their computing. And in fact, your modern laptops and that sort of thing typically have 4 or 5 or 8 or something of them in. How many do you think a modern supercomputer has? And this is you have no particular reason to know, you just might be interested. And it looks like the fourth item in the poll might have gotten messed up. It was supposed to be, let's see, 1 million. So
my apologies.
Item 4 in the poll is 1 million, and go ahead and make your choices there, folks. Oh, it looks like they mostly have, and maybe there was a little confusion about those last two. So I think I'll just skip right on to the answer whenever you want to shut it down, Bruce. And let's see if my PowerPoint is still here. Yes. So the actual answer is more than 100,000. Let me find my bit of note that actually told me 145,000 and some odd number are what they've got in our supercomputer, which is kind of boggling just to think of how many of those are likely to fail on any given day and need to be taken offline and at some point replaced, and all the just crazy stuff behind that. So anyhow, just a little bit of trivia related to modeling to throw at you that your students might find interesting. Let's move along. The other aspect of why NCAR is pretty big into the whole modeling world is, besides running a supercomputer, NCAR is sort of the caretaker for a couple of major, essentially open source climate models and weather models. It allows a large national center to build the basic model and then allow university researchers or various researchers who don't have quite the facilities to build a whole model from scratch to tinker with some aspect of it. So for example, if a group in Finland really wanted to improve the sea ice aspects of the model, they could do that, plug it into the overall model, and use the general open source model by NCAR with their sea ice module plugged in. So modeling is a big part of what we do here at NCAR. Some examples here, the upper right is, I believe, carbon dioxide. flow around the globe, the red there. The lower right one is actually a model of a sunspot. The left one I'm not quite as sure of. I think it's pollutants mixing, but it was a pretty picture. I'm going to jump ahead now, or move into sort of the theory part of the talk, and I promise this won't go on and on. I'm much more into showing examples of things, and I'm going to try and make the bulk of the talk around that. But wanted to ground things a little bit, and particularly referencing the next generation science standards and what they have to say about models and modeling and what students should do. So one of the things that they bring up is the notion of the difference between mental models and conceptual models, and I'll describe in the next slide what I think that distinction is from reading through their materials. They then go on to say that most of the emphasis in the next generation science standards and in the practices, particularly the one that references modeling, that they are talking about conceptual models, and they then further subdivide that into a number of types of models, most of which will probably be familiar to you. So one thing that they consider a model is a diagram. Often they show connections between things, relationships, and so forth. Certainly you're familiar with that. Physical replicas and scale models, so anything from a toy car or a physical model of the heart or anything of that sort of nature. Oops, went backwards. Go forward. Another type of model that they talk about is mathematical representation. So if any of you have done work with predator-prey models to see how the bunny and wolf populations tend to fluctuate together, that's the kind of thing they're talking about there. Oops, I keep going backwards. And then another type that they reference is computer simulations. And that'll be what I spend a bulk of this webinar on, although I've got some physical hands-on things and different other things to point to as well. Obviously, mathematical representations and computer simulations are pretty closely tied together. I wouldn't quite say you can't have one without having the other. Certainly you can have math models that are not represented via computers, and you can have some computer simulations that aren't particularly mathematical, but usually they're pretty closely tied. Let's see, a little bit more about this distinction that NGSS makes between mental models and conceptual models. You can read here the quote that I pulled out. What it seems to be saying to me is that students have mental models in their minds. People have mental models in their minds. There are ways that we cope with the world. There are ways that we make sense of the world. They may not be the same model that somebody else has in their head. An example that I tried to pull together of this was, imagine a fairly young kid, a toddler, who's seen little critters around their yard, and maybe they even have a pet one in their house or something of that nature. And they're these funny little things that move around pretty fast and have a strange kind of fur that's actually feathers. They have sort of odd mouths that are different from other kinds of animals. And one of the things that they point out in the NGSS definition is that it's a functional model. So for example, if I, as a young toddler, like to chase small animals, well, I know that if I chase one of these, they'll just fly away. So it's functional in the fact that I can identify it as a thing that I'm probably not going to catch. It'll just fly away. Now, somewhere down the road, I may, oops, if I can get my cursor back here, I may, as a young kid, encounter some other things that I'm not quite sure if they fit in my model of what a bird is. They don't look like small things. They do have that funny fur that the other types of birds have. I wonder if they can fly away if I were to chase at them, and so forth. So anyhow, I think that's kind of what they're getting at of a mental model. It's sort of the model in your head or in your students' heads. Most of their emphasis is instead on looking at conceptual models. And these are, I think, what we mostly think of as scientific models. They're things that are shared that people can discuss. They can maybe use the math of or visualize, make representations that people can communicate with and play around with and that sort of thing. An example might be a diagram of the water cycle. It shows the parts of it, it shows where things move, and it's sort of an agreed upon thing that we can both look at it and say, yeah, I know that rain sometimes falls over the ocean and sometimes it falls over land. Let's see. So I'll just go through quickly the different types of conceptual models. I think this is just valuable because model is a word that gets used in many different ways by many different people. So to have a little bit of a vocabulary of different types so that as we move forward, that maybe helps you think about what you want to do in the classroom, which of these types you want to engage with, which are appropriate for students of the age that you're working with. So the first one they mention is diagrams. Clearly they can have parts labeled so that you can tell the different pieces of things. They can sometimes be to scale so that you can tell, for example, that the crust of the earth, even though it seems like it's a big thing from a human perspective, is really quite small compared to the size of the earth. Diagrams often have arrows showing connections or motion or some other relationship between things. And they often also sort of show time passing. So this one is kind of showing the formation of a cloud, and each of the steps with the arrows is kind of meant to be essentially a time-lapse movie in our head. Another type of model is physical replicas. Clearly things like, cars and that kind of thing, scale models, and with younger kids sort of saying, okay, if you put a person here, how big they should be, to help kids get that sense of scaling and proportional scaling between different things. You may have seen a scale model of the solar system. Here's one that's on the campus at University of Colorado. There's the sun right in the top of that pyramid. It's sort of a goldish sphere, and then they have spread out across campus at relative distances. The inner planets are on those plaques, pedestals just behind there, within a few feet of the sun, and then the other ones are half a mile away, or as you get further out in the solar system. So that's a scale model. And then in terms of motion, once again, a model of the solar system that doesn't show things proportionally to their distances, but an orrery like this shows their motions and maybe gives you a sense that the ones around the in closest go around faster and that sort of thing. Let's see, mathematical representations. Again, predator-prey models are a real common one that you may have seen of that, but I think they mention in the NGSS the gas laws that say if you change the pressure of a gas, what happens to its volume, and things of that nature are another good example of a mathematical model. And then computer simulations. I think that's fairly self-explanatory, and as I mentioned earlier, pretty closely related to the mathematical models. Most computer simulations are based on a math model. I'm not sure I'd quite say all, but I would say most of them. I think I skipped over analogies. I figured that was fairly self-evident, and I don't have a lot else to say on that. Most of the rest of the webinar I'm going to devote to showing a lot of models. Most of them simulate computer-based simulations, but in many cases with partner hands-on activities. So let me dive into that. I think I'll do a poll question in just a second here, but I think I had one or two more notes on theory before we get into that. This is my second ugly all-text slide. I don't think I have a third anywhere in here. A little bit more on the soapbox. I think it's really important to have students behave like scientists, so running models, not just being told about them. I think there are a number of topics related to modeling that I'm not going to get into that much because I'm focusing more on the computer-based ones, but I think it's really important, and it's just not my area of expertise and sort of a time constraint, to have students construct their own depictions of systems and models, concept maps, things like a drawing of the water cycle like we saw earlier, things of that nature. Building up those models in their heads is really valuable. I'm not going to say a lot more about that, but I acknowledge that that's critically important. I think the other bits, I'll guess I'll go a little bit more on my soapbox that although I think diagrams like the water cycle one or that food web one that I showed are good as far as they go, often those just have sort of generic arrows connecting things that say, okay, this is somehow connected to that thing. But what they often miss is sort of the strength of that connection. The amount of water falling as rain over the ocean might be depicted as the same, as a similar sized arrow as the amount of water flowing from snow melt into streams, when they might actually be very, very different. So to me, having diagrams is great as far as it goes, but having models that you can run and that do behaviors, I think, get at a lot of things that diagrams don't. Finally, I'll just say that some of the stuff I'm going to cover in this webinar may well be a bit advanced for elementary students. Partly, it's a little bit tougher to find good material at the elementary level. Partly, I want to give you as educators kind of a sense of what you might be preparing them for later. So even though you may not teach algebra or trigonometry in elementary school as a mathematical equivalent of this sort of idea, you do want to know that algebra and trigonometry exist and that their middle school teachers will be addressing that and will need the students to have good solid arithmetic foundations to take that on. I think similarly, if you kind of know what's coming ahead for them, you can make better choices as educators about what you cover and how, sort of looking down the road on behalf of your students. Let me do one more slide and then do a poll question. I mentioned I'm not going to do a lot with students building their own models and thinking about that kind of thing, but I will put a plug here for a book series that has a nice exercise around that. One of my colleagues, Lisa Gardner, has been involved with writing a series of books called Elementary Globe. If any of you are familiar with the Globe program, it's one of the older citizen science programs where kids collect data, they take readings of rainfall or of stream pH and load those up onto a website and share that with people around the world and do experiments or do analyses based on stuff uploaded by other students. Anyhow, they've done a series of books to go along with that curriculum. And there's a nice piece in there kind of showing not exactly a food web, I guess more like an energy web of what's the connection between a plant that a kid can observe and other parts of the sort of Earth system. So that's a good, very elementary friendly, both series of books, and that particular activity is a nice one. Let me go back a second and pause for the second poll question. And Bruce, if you could pull up the one about, do you currently use simulations or models in your teaching? So now that we've sort of talked through what NGSS and what I might consider a model, I think this is, up to you what you consider a model, or a simulation, and just how much do you use that? And it looks like an interesting sort of spread here. We've got about a fifth of you are using them a lot, and some sort of at the other end of the spectrum, hardly at all, and quite a few various levels in between.
We'll just take a moment for folks to continue with the poll because, Randy, they can't see what you're seeing.
Okay.
So if everyone could just go.
That's changing anyhow.
Okay. You just take a second to complete. I think that most people have voted. We're going to close the poll now, and let's see how people voted.
So some people aren't really using models or simulations much at all, and I imagine you're probably using some diagrams and things like that. So to some extent you are a little bit, but looks like quite a few people are using them a bit, a handful of times throughout the school year. And then there seems like there's sort of a gap, and there's some people who use these things quite a bit. So that's kind of intriguing. So hopefully those of you who aren't using them will find something today that can help you out there, and those of you who are can find something else that you can use. Okay, let's see. All right, my last theory slide, and then on to examples. Oops, where did my cursor go? There we are. So one really powerful notion that I always bring up when talking with any educators about modeling at any level, there was a system scientist named George E.P. Box who worked for, I think, the Bell Labs or somebody like that back in the 50s. Had a great quote that was essentially, all models are wrong, but some models are useful. Now, some people prefer to say all models are limited or all models are approximations instead of wrong, because some people will take wrong a bit too literally. But his point was that they're all approximations. They all have limitations, that they aren't the real world. And that's critically important to understand them and what situations they will do a good job in and what situations they'll fail in, or they won't be very much like reality. And it emphasizes in the but some models are useful, that not all models are useful. Some of them are a model of something that's just not really anything that tells you anything of value, or it's so inaccurate. So that's an interesting thing to keep in mind, but the key thing is to find the models that are useful and to talk with your students about the fact that they are not reality, they are not perfect. NGSS has a fair amount to say about this. I plucked some things. Looks like pages 56 through 58 is where they really talk about the practices. And they say a lot of things like do not correspond exactly. It is important to recognize their limitations. I think to talk about their intrinsic limitations. So NGSS makes a pretty big deal out of this too, to really help students understand that models are not reality, they're a representation, and they're always approximations. Last notion of strategy before jumping into the examples, I think particularly at the K-5 level, it's really important to not be too abstract. So if you use mathematical models or computer simulations, you really want to make sure to tie them to some concrete, physical, real-world examples that kids can touch and see and that sort of thing. I think it just makes things a lot more realistic to them, makes the believability of the models much higher if they've seen something similar, sort of for their own eyes to begin with. So I'll be showing a little bit an example of a tree ring simulator that does that sort of thing. Also show you some glacier related activities that kind of tie a computer simulation to some more hands-on activities. Without further ado, I'm going to jump into a bunch of examples now and just run through a number of things that I think you might want to use. And let's see. Carla, I think at this point, I don't know, I haven't been paying attention if you have been, but most of the slides going forward will have URLs down at the bottom of where to find this stuff online. So if you could do some pasting in there for me, that would be awesome, so that people have access to that.
Yeah, Randy, I have been pasting in as you go.
So. I figured you probably were. Thanks, Carla. Mm-hmm. Okay, so let's see. So one example, how do we know about climates of the past? And you may or may not even talk that much about climates with students at this age. It may be more of weather, but certainly they're going to get that by middle school. So just thinking about, hey, what was the past like, and was the weather always the same, and was it rainier some years, was it warmer some years? And people are pretty familiar, even young kids probably have at some point seen a branch of a tree sawed off or something and have seen these rings on trees. So getting some physical examples of tree rings and tree cookies is what the people in the field call just a little slice where you just take a thin piece off of a branch or off of a tree. I found that Christmas trees are a really good source of this. They grow fast, so they have big rings that are easy for little kids to see. They don't have that many rings because they chop them down after 10, 12 years, so it's relatively easy to count and that sort of thing. And after Christmas, if you grab your tree and lop off a half a dozen of these just off of the base, you've got a classroom set. So having kids physically look at those and just count the rings and get a bit of familiarity is a lead into this tree ring simulator that we've got. So the idea here is that we're giving students sort of a half of a tree cookie, which is over on the right side here, and we're asking them to decode it, which sounds pretty cool, to try and figure out what the climate was or what the weather conditions were over the lifetime of this tree. So they get to build up their own matching tree ring half on the left side by choosing the conditions and gradually growing rings. So we'll start off, we'll assume that the conditions were normal this first year, and I'm going to press on the Grow New Ring button, and you'll see a ring appear over here that hopefully matches our cookie that we're trying to decode. So if I click the first one, oh good, we got a match, so the conditions were normal in that first year of growth. Well, let's try adding another one, and let's assume they were kind of normal again. Uh-oh, if you look closely, the ring doesn't quite match. So we'll go up, take that ring off, and let's see, maybe it was dry that year. Let's try changing it to dry and adding a new ring. And that one doesn't quite fit either. So we're running out of choices. We'll remove that ring. We'll come down and say, well, let's try wet and grow a new ring. Wet it is. So now we've got 2 years of the life of the tree decoded. We can see it started off kind of normal. It had a wet year when it was just a baby there. And we can go on like this. Let's see, I'm trying to remember. Yeah, I think I do a little bit more. Nope, okay. So then we've got another normal year. We then have a dry year. And I'm gonna not go through just sort of trying to guess. I'll just give you the quick answers here. We have another normal year. We have another year, I think 3 in a row of dry conditions, so they're narrow rings, 3 in a row of wet conditions, so wider rings, and then a mix as we go out through the rest of the lifetime of the tree. So now we've got a graph, and again, depending on what age your students and what they're capable of, we've got a fairly simple graph reading exercise, and we can bring up questions like, was it wetter in the early part of the tree's life or in the later part? So if we look over here, we've got some pretty dry years early on, and we've got a lot of wet years later on. So we can look at those kind of questions. Let's see, what else did I want to say? I think that was the gist of this. Now that might be about as far as you want to go with elementary aged kids, just to get that kind of a correlation. You have the option in this interactive to go to another level of it and do a same sort of thing with temperature. So we can grow rings. And I think in this one, I've just got it set up so that I'm just showing all the right answers. But I think there's a normal ring, and then we have a warm year ring, and then another normal year and another cool year. And then I think you just sort of run them all out and again, decode the pattern. And you can ask similar sort of questions. Were there any long heat waves? Were there any long cool spells? Has it mostly been warm, cool, whatever throughout the life of the tree? Again, you may or may not want to go into this with young kids, but it's another factor that can influence how plants grow. Finally, this is where it gets a bit more complicated to have both the moisture and the temperature playing in. So both of them play into the width of the rings. And this gets fairly tricky. Again, maybe or maybe you're not. You want to do this with elementary kids, but this is maybe an area where you let the kids who are ahead go ahead and try something a little bit tougher. So again, we're doing combinations here. So sometimes you might have a warm year with normal moisture. You might have a wet year with normal temperature, and so on down the road with all kinds of combinations of this. I'll just click through those to give you a flavor of it. I think one important thing, as well as doing these sort of prescribed lab kind of activities where you're telling the students what they're trying to do and what they're doing is trying to get as an outcome, is to have them just sort of play. So part of this interactive has a section called the sandbox, and that's meant to be like a kid's sandbox where you go in and you play with the sand and you do whatever you feel like. So this one, instead of trying to answer a particular question, you can just sort of build tree rings and build trees however you want. So you can pull up, using this menu in the upper right, some samples. I've pulled up a sample here that's normal growth in all 15 years of the tree. And now we can make unusual combinations and sort of compare that. So what if we make it so that we find the best growing conditions, which turns out to be normal temperature and a bit of extra moisture, and we just make a whole bunch of rings like that? Well, it looks like by the end of 12 years, we've got a tree that's as big around as a normal one would be. At the end of 15 years, we've got one that's even bigger and going off the screen. That's something that a kid might want to try and play around with. We can do other things where what's the worst growing conditions, which turns out to be dry and cool. And we make a whole bunch of little rings and end up with a tree that's only about half the diameter of the normal year's one. And I'm trying to remember what other examples I gave here. This one, oh, okay, this one I did very wet for a bunch of years and then very dry for a bunch of years, so you can sort of visually see the difference in the width of the tree rings. Anyhow, the point being that play is an important part of how particularly young kids learn, so that part of this activity is go in and do something specific, but part of it is around the notion of, hey, go in and play around if you have some free time, if you're doing this at home, if you got done with the activity early and you just want to mess with it, and interesting things can come out of that. So let me jump on now and take a quick reminder at my poll questions to see if any of them come up yet. Nope, okay. So here's another activity where I'm trying to pair something that brings physical, non-computer based things together with a computer simulation. So in a minute, I'll show you a simulation of a glacier that's made by a group at the University of Colorado that does all kinds of simulations. PhET is the name of the group, P-H-E-T. You may have run into their stuff. But before that, it struck me that it'd be nice to get kids a sense of what a glacier is and some familiarity with them. One of my colleagues here has created an activity called Glaciers Then and Now, where you're given a series of printout pictures of glaciers from about 100 years ago, so old black and white images that somebody took. And then more recently, somebody came around and tried to find the same location and take more or less the same picture sometime within the last 20 or so years. And here's an example of one of those. And you can see if you look around a bit that, yeah, the mountains are still there and the spots are the same, but not all the glaciers are quite where they were. Some of them have melted and receded and that sort of thing. So this is a nice just picture map matching activity. You print out a bunch of these, you look at them and you try and match them up. So just to get a familiarity with what a glacier is, what it looks like, and do something physical hands-on beforehand. Another somewhat more involved activity, but really fun, is called Model of Moving Glacier, or Glacier Goo for short. In this, there's a formula for mixing, I believe it's just normal like Elmer's glue and borax, and you get this sort of goo flubber kind of material that flows slowly. And I believe a grad student at the University of Maine or somewhere thereabouts worked with one of my colleagues here to write this up as a middle school type of activity. I think the original version had been done at the college level. But anyhow, it's just you basically make glaciers out of this goo flubber stuff, put them in PVC pipes that are tilted. She's done it with a clear plastic one, but it works for illustration in these diagrams, but you can use just the normal white plastic stuff. But it basically lets you show you how something slowly can flow and what that looks like and so forth. So again, a little bit more involved, but a really concrete physical activity that you could do with students to get them a sense of what a glacier is, how it moves, before jumping into the simulation. Again, the simulation is available from the PhET program at University of Colorado. They've got a huge library of all kinds of different simulations. This is just one of many. And I wanted to jump back into theory mode for just a moment before I talk about this in particular. And then I'll show you the examples of what kind of things you can do with the interactive. But I couldn't find my original source on this, but I remember in a seminar years back, somebody made a really nice point of sort of the different levels of interactions one could do with a model or simulation. And I'll talk more about that as we go through the webinar and try and mention it a bit more as we talk about the glaciers here. But there's one level where the student just runs the model. They basically just hit play, make some observations, maybe record some data, and that's sort of the base level, get started with it. You can then step up to a little bit more, I don't know, intellectually sophisticated way where they start changing the parameters. So with the glacier one, we'll do things like changing the snowfall rate or changing the temperature and make different runs. So that's a little bit more sophisticated of making some choices there. You can get into even more sophisticated things where you start modifying the model. So not all of these computer simulations allow that, but some do. And you can go in and change how the relationships between things are. If you make your own models, like in a spreadsheet or something, you can certainly do that. And then the highest level that they mentioned was constructing a model from scratch to make one your own. Spreadsheets, again, are a relatively easy way to do that. If you're familiar with some of the block programming languages that are young kid friendly, like Scratch, that's another place where you could potentially get into building models with kids even at the elementary level. And I don't think you necessarily have to get through all of these levels to get value of it. But again, I think it's something to just be sort of aware of in your head of what is it you're trying to do? How hard might it be for the students? Should you maybe scaffold things a little by, having them run a model before they start adjusting things or something like that? Let's see. Okay, let me show you the PhET one, and I'm realizing my time's getting a little tight, so I think I'm gonna go a little more quickly now. This one, so they basically have this glacier sitting here, and they've got a number of tools that you can use with it. The main thing that I'll show is that you can change the air temperature and change the snowfall rate. In terms of the tools, you can take a flag and drop it on the glacier. I'm not running any of these. I just should note that because Bruce warned me that sometimes bandwidth and playing anything that moves in these webinars doesn't work out very well for some viewers, I've avoided actually showing these models. Most of these are animated, including this one. So if I were showing the real thing, the glacier, the flag would move down, and there's some little stones included as black dots in the glacier, and you'd see them move and so forth. But in order to make the technology behave on a webinar, we're skipping that. So I'm just going to jump ahead to where the flag has worked its way down the glacier. If you look closely, you can see it's also sort of worked its way from the surface down into the glacier a ways. And you can also see some of these rocks have sort of built up at the terminal moraine, the bottom end of the glacier. So there's really all this stuff moving, but the glacier itself kind of stays in place, which may not be intuitively obvious or sensible of a thing to young kids. So it strikes me that even fairly young kids, if they get the idea of more or less of what a glacier is, and you say, gee, what if it got warmer? What would happen to the glacier? I would expect a fair number of them would get somewhere near the idea of it's gonna melt some. Oh, one more tool, just a quick mention. So they also have these calipers that you can measure size and thickness of things, and all these other things are pretty fun to play with, but not essential to the story I'm telling now. So let me get back to the glacier. Let's look at changing the temperature, and I'm just gonna turn it down, or excuse me, turn it up a very slight amount. And the glacier melts quite a bit in some sense, which might be what your kids would say. but it doesn't melt all over. It kind of melts at the bottom and recedes. And that may not be obvious. It may be sort of partly in between what they would expect and would have hypothesized and what they actually see. Likewise, we can turn the temperature back down, and the glacier gets bigger because it's colder and more snow can accumulate and not melt. Same sort of idea. We'll put the glacier back to where it was and now mess around with the snowfall rate. And again, maybe all you want to do is air temperature, depends on your kids, depends on their age, but maybe you want to bring in a second factor and say, hey, if it starts snowing more, or let's see, I think I have it snowing less at first, what's going to happen? The glacier is going to get smaller. If I have it start snowing more, the glacier is going to get bigger. So just simple basic things like that of bigger, smaller, more or less kind of relationships. Okay, let me do this one and then reassess time. This is one of the more critical ones to get at that essentially all models are wrong, some models are useful. And this is not inherently a computer-based activity. This is one that you can do with just a checkerboard and some cutout pieces of paper. We've got this a write-up of this on our website, or the URL I think is on here, and Carla hopefully is plugging it in. Let me anyhow just explain what's going on with this. It's basically a food chain / food web, and you play out the game, but the rules of the game are really pretty bad and inaccurate as far as modeling a realistic system at first. And the whole point of the game is to have the students play a few rounds and say, wait a minute, this game's not very good. And then say to them, how would you make the rules better to make this more realistic? And then have them modify the rules, play it a bit more, and then say, wait, our rules still aren't that great. Let's try this instead. And so this is getting at that notion of actually modifying the model and paying attention to what's not quite right about it. And this could be done easily with just about any food web, food chain. So if you want to do it, if you're far from an ocean and your kids aren't familiar with that kind of thing, but prairie dogs and wolves and whatever are something that they are familiar with, it could easily be done in just about any sort of setup like that. The basic idea is that you have 4 players. One person plays the diatoms, and they put some of the diatoms out on the board. You use a normal checkerboard. I've only shown part of it here just in interest of space, but you'll get the idea. You have another student play the copepods, which are small crustaceans that eat diatoms. And then they put their game pieces out on the board. You have herring, which, surprise, surprise, eat the copepods. And then orcas, which eat the herring. And each turn, each player can move one of their pieces, except the diatoms, because they just float. If you're the diatom, you got the short end of the stick in this game, and you figure that out pretty quickly. You can move, so you might want to flee from something that's getting ready to eat you. Or if you're near something that's food for you, you can jump over it and eat it and reproduce. So those are the basic rules of the game. There's some stuff around what happens near edges of the board and so forth, but that's the basics of it. So we'll start off having this copepod in the upper left corner after the diatoms had their turn and did nothing because they just float around. This copepod sees a diatom right next to it, so it's going to jump over it and eat it. So the diatom's gone, the copepod jumped over it, sort of like checkers. But whenever you eat, you reproduce. So now there's a new copepod where the diatom was. So we can do that, move on. The herring now has its turn. It jumps a copepod, reproduces. We now have more herring. But then we've also got an orca that can jump over a herring and eat it. And we've got new orcas. Long story short, after you play a few rounds of this game and you kind of keep track of populations of different things as you go, you start to see that there get to be a lot of orcas and there get to be not so many diatoms. And after a few more turns, you get an ocean full of killer whales, and there just aren't anything else left because the whales don't die, nothing eats them. The diatoms couldn't reproduce because they couldn't eat anything. and eventually the orcas just eat their way through the food chain. So anyhow, it's a bad game. After you play it a few rounds, you fix it, and that's the key modeling sort of aspect. I think that's all I want to say about that in terms of time here. Just to reiterate how that's such a big part, that improving games or realizing their limitations, I guess both aspects of that, or in the sense, in recognizing the limitations of a model and improving it, is really what we're going about here. I'll make a couple of quick mentions of things that you might want to do in companion with this. There's a sort of physical run around activity game called Oh Dear that I've seen a number of different versions. If you just do a Google search, you'll find it. You'll find videos about people doing it. It's basically, some people are deer, some people are sort of parts of the habitat that they need that are either food, water, or shelter, and you run around and try and match up with things you need. So it's getting at these sort of food chain, food web kind of things, but it's a physical, get up and move around activity that might nicely complicate it the more sit down, play the checkers. And it struck me that if you're at all familiar with predator-prey models, and I think my next slide says a little bit about that, so I'll describe that briefly if you're not. It seems like you could do a predator-prey system very similar to food chain checkers and have kids come up with what the rules are for how the predator moves and how it reproduces, and likewise for the prey. So yeah, as I mentioned here, I think I'll just be brief on that. If you're not familiar with these are simple models where you have a bunch of bunnies or something like that that gets eaten by a bunch of foxes or wolves or whatever it is that your predator is. And there's really interesting dynamics of, if at first there's not a lot of predators, the bunny population will explode because they've got plenty of food and not much eating them. But in response, you'll start to get more wolves because they find prey that they need to eat more plentiful and easier to find. And so they start eating, and they start having pups, and they start eating too many rabbits, and eventually they crash the rabbit population. They kind of eat themselves mostly out of their food source, and you have these cycles. So I think I'll pause as far as any further explaining that, but there's a lot of versions of that out there that might work well with both the Oh Dear and the food chain checkers. Let me pause here a second and check in with Bruce about how much longer we should go, because I see we're getting close to our time, and I've got way more slides than I'm going to do in 5 minutes. So I just want to get a time check. What do you think, Bruce?
You go, man. Absolutely.
Okay.
We're good till 5.
Okay, let me look a little bit ahead in my slides and see if there's anything that I want to jump ahead to. I'll just power ahead here for a moment and see what we get. We'll do another check-in in a few minutes. I'll be kind of quick with this. Molecules are, again, molecules and atoms and elements and compounds and things like that are maybe something you're going to get into at the elementary level, or maybe not all that much. Imagine your kids, at least by their time they're in 5th grade or something, will have seen some depiction of an atom or a molecule and somewhere along the way and have some sense of what they are. You can use your discretion of how much they know and how much you want to get into it. But this is one of those things that's specifically called out to some extent it's called out in the NGSS, and I think is clearly the kind of thing they'll run into in middle school and beyond, that there are a lot of different ways to represent a molecule, and we've got a kind of simple matching game here to play around with that. So let me just show you what this game looks like. Again, this is maybe kind of that visual literacy kind of thing that if you have them play around with young kids when they run into this later, they have much better sort of visual recognition of things and ability to pick it up. So this is just a simple flip over cards, memory matching kind of game. So I go in and I've got a grid of 4x4 cards. If I click any of them in the actual simulation, it sort of does this nice animation looking like a card flipping over, but for the screenshot, it basically flips over and says, okay, that's nitrogen dioxide. Well, let's see if we can find a match. I don't know where anything else is, so I flip over the next one. Oh, that's oxygen. That's not a match. Well, let's try something else. So as soon as I flip another card, those two get hidden, and I've got to try and remember where they are. So flip a next one. Well, it's nitrogen. I don't think any of those. That first one had nitrogen something, but that's not it. Let me try the one next to it. No, that's not anything we've seen before. So let's keep moving on. Flip one. Wait a minute. That looks familiar. I think I've seen that before. And if my memory was good, I come up here, flip over that one I've seen. And then because I've gotten a match, it'll make those two disappear. So this is really just sort of visual literacy, nothing really about that much about modeling. I mean, these are models of molecules, but we're not getting real sophisticated yet. Maybe it's helpful just to, have your kids familiar with what they look like, but maybe not. We're moving on to a more advanced level of the game. And here we've got a little bit bigger grid, which makes it more tricky, but it's about the same idea. We'll flip over one, flip over another one. No, those aren't quite a match. Move on down the line, flip over another one. Wait a minute, that doesn't look at all like what we've been doing. So in this case, we're playing around with the fact that there are different models to represent the same molecule. So if I'm moving further along down here, I get to a point somewhere further down the row and I found this. If I really know the different types of models, and again, I don't think most elementary kids are going to handle this, but by middle school they might, and some aspects of this they might pick up on if they play with. If I really know what I'm doing, I know that CH4 is the same as that thing. It's methane. The C is that sort of grayish one in the middle. There's 4 hydrogens around it. And those really are the same thing, even though they look different. The point here being that you can have different models of the same thing. They're different representations. Some of them are useful in different ways. Anyhow, those two would disappear because they were a match. And I'll just sort of play out a couple of slides that show what I'm talking about here. So at first we were playing the game where you had to make identical model matches. If you saw a ball and stick model of carbon dioxide, it matched with the ball and stick and so forth. The more advanced versions start saying, hey, this and this are models of the same thing. They count as equal. I think I'll go through this pretty quickly, just a few pointers to why this fits in with earth science. Obviously, carbon dioxide as a greenhouse gas, well, I guess my point here was still just on the models. There are different types of models of carbon dioxide. There's 2, there's another one, and they're all sort of showing different things and different aspects of it. The first one shows how many carbons and how many oxygens. The second one gets into their arrangement. The third one deals with their arrangement, also tells you that they're double bonds. So that's important as you get into more advanced chemistry. And the last one kind of shows the proportional sizes of the electron clouds around them. So all of them are showing truths, but they're showing sort of different angles of the truth. Again, pairing this with physical phenomena and that sort of thing. There's a lot of examples. Again, do a Google search on marshmallow molecules or something like that, and there's lots of groups doing things like that. This is stuff that you could have the kids physically put together and sort of relate to the models that they see on screen. You may have these MollyMod kits or something similar, or if you don't, again, probably pretty likely when they hit their first chemistry sort of course in middle school, they're going to play around with these things. So there's physical representations to try and get them to match those up with what they see on the screen. Why is that relevant in the earth sciences? Well, there's a lot of gases of different types that are different molecules in our atmosphere. What are the most plentiful ones? What are important ones that aren't so plentiful, so forth like that. One example is nitrogen. Why is almost all of our atmosphere nitrogen? Well, it's hard to break nitrogen. That model doesn't tell you that. That model doesn't tell you that. But that model says, wow, this is a triple bond. It's really stuck together well. It's really hard to get one nitrogen apart from another. So it just sits there as N2 in our atmosphere and doesn't go away. If you have them playing around with the MollyMod models, that's a tongue twister, they actually have 3 holes in the balls that represent nitrogen, and the bonds are triple. So if they play with that, it's hard to get them apart once you've got them together, and that might be an idea that sticks with kids. I think I'm going to be very brief, assuming you guys more or less know about greenhouse gases and that kind of thing. I'm not going to go into anything complicated. It's just that basic idea that sunlight comes in, goes right through the air and makes it to the surface, but once it turns into infrared, it has trouble getting back out and warms our atmosphere, because some gases absorb infrared and kind of act like a blanket, keeping some of that heat in. So again, some of the stuff about molecules and the shapes of them, certain things are greenhouse gases and the shapes of the molecules matter for that. Some things aren't, and the shapes matter for that. I think I won't get into any more detail than that there at this level, but just a quick mention of that. And I think I'll skip ahead on this one. This one may not be playing well. I accidentally left in a slide with motion, and I know with the folks with low bandwidth may not be able to see things. Those of you who can see the motion, we have an animation that kind of shows that a greenhouse gas like carbon dioxide can wiggle and vibrate in a lot of different ways, whereas simple molecules like oxygen and nitrogen can't. And that's a big part of the difference. So some of that stuff of the structure of them ends up having to do a lot with the properties of them. Okay. This was another good one in terms of the physical running around, sort of get up and move kind of thing. Cycles are a big deal. A lot of places in earth science. The nitrogen cycle and the carbon cycle are ones that we deal with a lot, but again, maybe aren't something that you're going to necessarily run into at the elementary level. The water cycle might be a good proxy for this, that I know is covered a lot of times at elementary, and might be a simpler thing to do. We have an activity on the nitrogen cycle. I'll talk you through that, but you could do a very similar thing with the water cycle, and I've got a couple of pointers. There's some groups that have versions of that online. I haven't looked at them yet, but that might help you out. So our nitrogen cycle game, the basic idea is that the student is a nitrogen atom. And instead of just looking at a diagram like this and saying, okay, where does nitrogen go? Well, it goes from plants into the soil, into microbes, and then maybe into the air, and just sort of following the arrows around. In the nitrogen cycle game, or traveling nitrogen as it's sometimes called, the students act as nitrogen atoms and they follow around. But it's not a straightforward, you always go here or you always go there. It's sort of random, because there's various places you can go. If you're in the atmosphere, you can get sucked up by trees, or you can be precipitated out by rainfall and so forth. So what we do is set up a bunch of stations around the room. And again, maybe think in terms of the water cycle for this kind of thing, if that's what you cover with your students. And so we just put a little placard on the wall. I mean, it's just a piece of paper printed out with the name of the place, and then underneath, and I'll show you this in more detail in the next slide, where you could go from it. So you might start off in atmosphere, you'd come up, you'd see where you can go, you roll the dice, and it might say, well, you get rained out of the atmosphere as rainwater, so go find that station. So the student would keep track of where they were. They have a passport that they carry around with them to sort of track their progress. And then they go find wherever in the classroom the rainwater station is. They go over to that and do the same sort of thing. Pick up the dice, roll them, see what they do next. They maybe end up raining down into the surface water, might get sucked up by plants. The plants might get eaten by animals. The animals might die, end up in the soil, and so forth. And everybody's favorite station that I had to throw in here, even though that's not necessarily next in the line, little kids love animal waste. So that's one of the spots too, and that's one of the places nitrogen ends up. So the kids get to one of these stations, and as you can see, if you roll the die, if it says 1, you go into a lake or a stream. If it's 2, you go into the soil, and so forth. So every kid carrying around their passport is going to go on a different journey They put a stamp in for their first location. They figure out where they're going next. So if this person went from surface water into live plants, they go over to that one next, get a stamp there, and I haven't jotted it in on the screen, but they would write down how I traveled. So plants sucked up water from the soil, and that's how I got from surface water to live plants and so forth. They might end up in animals and so forth like that. So I think you get the gist of it. The idea here is that they are up physically moving around. They are playing the role of the nitrogen atom, and everybody's path is a little different. So it's really interesting to compare at the end. Some people never visit a certain station. Some people go back and forth between certain places several times and so forth like that. Let me see if there's any of these that I want to skip ahead to get to other ones. I think I'm going to go quick through a few here. Another physical example of things that you can do, a simple thing that kids are actually familiar with. If it's a hot sunny day and you're out in the sunshine, if you're wearing a black t-shirt or you're wearing a white shirt, which is hotter and which is cooler? Most of them have some direct personal concrete experience with that kind of thing that could be helpful in looking at a simulation of what Earth's temperature is like. So we've got a simple simulation that basically takes advantage of the fact that sunlight brings energy to Earth and warms it up. When it gets warm, infrared goes out, and at a certain point you get a balance between the energy in and the energy out, and that's what decides what the temperature of Earth is. This is just a quick screenshot. I'm not going to really show you this in motion, but if you want to go play with this idea, basically what we have kids at a young level like this do is just mess around with the albedo or brightness or whiteness of Earth over on the right here, so they can come down and play with the slider, drag it back and forth and make it really dark or really bright or really reflective and white. And the temperature thermometer changes as you go with that. I think for young kids, that's about as much as you'd want to play with this. If you want to, you could change the brightness of the sun and see how that temperature would be too. I've shown it here with all of the math behind this, but there's a button here and the default is for that to be hidden. This is a nice feature for older kids when you really want them to be paying attention to the math. I think for younger kids, you just want them to say, lighter colored Earth, colder, just like lighter colored t-shirt keeps me cooler, darker colored Earth, warmer, and not get into too much beyond that. I think I'm going to skim ahead of these. If you are interested in some of these other ones, the PowerPoint's available afterwards, and I've got notes on where to find them. I think, Carla, don't bother trying to paste these in as I go through quickly. Other groups have taken on this similar sort of notion. There's one that's a really clever one where you can actually paint on your planet whatever combination of colors and brightnesses and darknesses, which is really kind of cool and kind of fun for younger kids. It's doing the same thing as that previous animation did, more or less, but it's a bit more interesting way of going about it. And that same group has a number of things where you can play around with build your own planets and change how far they are away and different things like that. So it's a more elaborate version of that. If you've got kids that are really digging that idea, that could be a place you could dig into. Going to do a quick few slides about the greenhouse effect. I think in the interest of time, I'm going to go through these pretty quickly. Again, grab my PowerPoint afterwards or listen to the recording if this was a part you're really interested in and I went too fast. But there's some really nice greenhouse effects simulators out there. The PhET group at University of Colorado has one, and another group called Concord Consortium in Boston has one. I'll just give you a quick drive-through tour of each of them. The PhET one, you can do things where, again, getting back at this notion of just running a model, you can just pick the atmosphere kind of composition. So this is showing it today. This is another one of those ones, if I was actually showing you the model, all the red infrared photons are bouncing around all over the place. All the yellow visible light photons are bouncing around, and you kind of can see that where the energy is flowing as it's moving. But with this, if you want to just run a different experiment, you can say click for 1750, the pre-industrial era, and it switches and the temperature goes down and there's not quite as much infrared because there's not quite as much carbon dioxide keeping it in. You can go even further back to one of the ice ages, and I think you can visually see that there's less infrared because there's a lot less carbon dioxide and the temperature has gone down. And I'm just trying to remember what else they have it here. Oh, and then you can do your own experiments where you just turn up the greenhouse gases or turn them down as far as you want. So here I've turned them way down and the temperature's gotten quite cold and there's hardly any infrared. Here I turned it way up and so the temperature's higher, there's a lot of infrared. So again, this is where you maybe have the kids do something simple, but then also let them play with it to just explore. There are other levels where they put in sort of virtual panes of glass to kind of carry that greenhouse analogy forward. I have mixed feelings about that, but you can play with that if you want. They also have a build your own atmosphere where they have this kind of heat lamp that shoots out infrared particles all kinds of directions, and if it hits a greenhouse gas, it makes it wiggle and then it shoots off wherever. If it hits a non-greenhouse gas, it just passes right through it. So that's kind of neat too. Concord Consortium also has a greenhouse effect one. It's got a bit of a different emphasis. So they add greenhouse gases by having a volcano erupt. Again, one thing you can do is just sort of run the model and say, you know, have the thing erupt once and see what happens, or you could have kids do a more elaborate experiment. One really neat feature of this one is, let's see if I've got it here on the first slide. Oh, okay. So what's going on here? We have yellow sunlight photons that come in from the top of the screen. They hit the ground, and if they hit something that's bright and reflective, they just sort of bounce off and go back up into space. If they hit something that's a little darker, they get absorbed and become one of these red heat particles that bounces around in the ground until they eventually work their way back up to the ground and they become an infrared particle, so an infrared photon. So we're dealing with a lot of energy transition here, which is an interesting thing, and obviously the kind of thing that with young kids maybe takes a little to get across. Anyhow, some of those infrared go straight up out into space, but many of them go partway up and mysteriously bounce off of something and come back down. So if you run this as an animation, and again, I can't do that in the webinar safely, but you'll see things moving all around, but they have a really neat feature where you can track a particle. So if you hit the, where was it? Oh, okay, since this is a screenshot, the stop falling button would have been follow particle or something. So it starts falling a photon as it comes in. If the photon bounces off the surface and goes out, you can see that. But if you follow another one as it's coming in and it gets absorbed, you can kind of watch it. It's being highlighted by the circle, and now it's one of these red things bouncing around down in the ground. Eventually it escapes as an infrared photon. Some of those end up bouncing back down and turn into the red heat in the ground again. But some of them eventually, and they all eventually get out and go back into space. So energy conservation, energy switching from one form to another, and just sort of seeing how one part of a complex model is behaving are some really nice features of this interactive. I think I'm going to be really brief on this. This might be a bit out of the range for most of your kids, but they do have one where you can do experiments. So you can start off with very little carbon dioxide. You can make the volcano erupt and send some of these green carbon dioxide particles into the atmosphere and see that the graph of the greenhouse gases starts to go up. After that runs for a little while, we see that the temperature has gone from somewhere about -2 degrees or so to somewhere up here in this +2 or 3 degrees range. We can run it some more and give another blast of carbon dioxide, see what happens then. And the scale changes as the animation runs, so it sort of auto scales the graph, so it may look a little different here from the last screen. But basically, we can then see that we started off with this kind of a temperature level, -2 degrees or something. When we added some greenhouse gases, it warmed up somewhere in this 1 to 3 degrees range. We added some more and it heated up some more. It's not like a perfect number that we can just say, well, it's 9.7 degrees, but it's definitely warmer than it was before. So this is a nice little thing to play around with conceptually. All right, Bruce, I'm on the home stretch, but checking in on time again. How should I do with this?
Well, we've got about 5 minutes left, and we do want to make sure that Carla has some time to tell everybody about the post-webinar discussion. So I'd say if you can hit this in about 1 minute, I'd say go for it.
I'll give you the blast through. This is a simple model where you can play around with what might happen in our future because humans control emissions, but the output of that is what happens with temperature. You can do some what if experiments, and there's too many slides for me to try and go through this and make any sense of it. So I'll just say it's pretty well documented in the PowerPoint. A lot of people like this model, so if you're at all interested, go check out the PowerPoint after the webinar. And I think it's pretty well explained there through a series of slides. And I think I'd just do it an injustice if I tried to rush through it. I will skip ahead to one other slide that I wanted to mention before we leave. And this one, I don't think I actually got the URL into the version that I gave to Carla, so let me paste it in. I'll close with the note. Oops, I gotta jump to that slide. How do I get there? Oh, I gotta stop. Come on, stop. And then go there. Oops. Sorry, fumbling a little. Okay, stop it. Nope, that's not what I want to do. Sorry, guys, I actually am technically competent. Okay, stop that. Go to that. Oops. Escape. Go to that. Then restart it. Make sure it's on the screen. So as sort of my, oh geez, sorry, grabbing a URL to paste into the chat, and I guess it hides my PowerPoint every time I do that. I've been interested in this topic of simulations and games for quite a few years. I've kind of collected something like Consumer Reports or Literature Review, or just a collection of a lot of things that I've seen that are relevant to the earth sciences. Some of them are well known, like the PhET collections or NASA Climate Kids or something like that. Many of them are a little obscure, but some of them are really good things that I saw at some conference, and they don't seem to be disseminating it that broadly, but seemed pretty cool to me. I'd say maybe a quarter or a third of these are well suited to the elementary level, but there are some that are sort of, you know, play a mini SimCity kind of game that deals with climate and your energy choices and how many coal plants you build or whatever. So there's a lot of fun stuff there. I've made this compendium and I'll post into the chat here. It's just a long page with brief descriptions of these things and links out to them. So all kinds of different sources that they're from, and far beyond what I could cover in this. So I'll just paste the URL in and stop there and let you guys deal with the rest of the webinar. Thanks, everybody. Thanks for attending. Thanks for your attention. And thanks, Bruce and Carla, for your flexibility.
Oh, absolutely, Randy. And thank you. We really appreciate you being able to take time out of your busy schedule and just share some of the broad knowledge that you have within this subject. And just so everybody knows, Randy has actually been involved in much of the design and the implementation and the testing of the resources that you've seen. I know we have a short time in front of us. So I just want to say, please go to your email. You've gotten a link to the post-webinar poll. Really appreciate if you could complete it as soon as you can after this broadcast. Also, I just have some information about the online discussion, which Carla, if you can unmute yourself.
I think so. There we go.
Very
Can you
good.
hear me?
Yes, thank you.
Okay, so after the webinar, you have an opportunity to join this online discussion where we'll continue the conversation, maybe share additional resources or ways in which you've used these simulations and games in your classroom. If you contribute to significant posts, by that we mean more than just simply saying that's great, but actually sharing something. If you do that within the next 2 days, so by end of day on Thursday, and that's midnight, whatever time zone you're in, you can earn another hour of professional development, contact hour of professional development. We'll give you a certificate. Next slide, Bruce. So to do this, I pasted the URL into the chat, but it will also come out in an email, or probably already has, from Bruce. And to participate in this, you do need to be logged in with a CERC account. There's a little prompt at the bottom of the discussion threads that will say, in order to do this, you need to be logged in. Once you click that, you can either log in if you have an account, or you can create a new account. And it's very quick and easy. It'll simply ask you for first name, last name, email, address, and you're good to go. Tonight, our facilitators, and actually through the week and even last night, are Aida Awad and DJ Cast. They're both extremely competent. Aida was a 2016-17 Einstein Distinguished Educator Fellow, also is past president of the National Association of Geoscience Teachers, who NESTA works very closely with. And DJ Cast is the Joint Educational Project STEM Program Manager and USC Young Scientist Program Director, and does a lot of work with elementary and young-aged kids, and has a lot of background. She's also a former Planet Stewards and is phenomenal. So we're pleased that they're facilitating these discussions. The last little plug I'll make before Bruce goes on is that if you did not see yesterday's webinar, you can still do that. You can still see it. The webinar is on the discussion page, and you can participate in that discussion and still receive an hour of professional development if you do so by tomorrow evening. And I also put that link into the chat as well. And I'll turn it over to Bruce.
Thanks so much. And if anybody has any questions or issues in terms of logging in, please definitely contact Carla. That's Carla _ McAuliffe at TERC .edu, as you can see on your screens right now. For those folks who joined late, I just wanted to remind everyone that we have 2 additional webinars in this special series, both tomorrow and on the 27th, on Thursday. And if you have any questions about that, you can go to the NOAA Planet Stewards upcoming events page, which the URL is down there. You can just Google NOAA Planet Stewards, go to the upcoming events page. You will see all the information and registration. And just as a note, the next NOAA Planet Stewards Book Club will be on Monday, October 2nd at 8 p.m. Information is also on the upcoming events page, along with, and don't forget to join us for our next webinar, the Teacher-Friendly Guide to Climate Change, on Tuesday, November 13th. I am going to I'm just going to go up here a little bit and make sure that everybody has the link to get to the post-webinar online discussion. I will be distributing this link and information in an email, which will be coming to you this evening as well. But if you want to get a jump on it, you can go to this right now. And if you have any questions, again, please contact Carla. And with that, I would very much like to thank you, Carla, for helping us organize and support this webinar. I'd also like to thank Randy for your time and energy in presenting this evening. And I'd like to thank all of you educators who have come to join us this afternoon. I look forward to hopefully seeing you tomorrow and Thursday. Last words, Randy or Carla?
Just thanks. Thanks for everybody's attention. I guess I'm passionate about this topic. I think, getting kids, this is real science when you start talking about how to model things. So I think NGSS is onto a great thing of emphasizing this. So thank you for the opportunity to share my passion about it.
I will put I just copied everything that was in the chat into a Word document, and I will attach that to a post in the online discussion if you didn't have a chance to explore some of these.
Very good. Thanks so much, Carla. I appreciate that.
Mm-hmm.
All right. And with that, I hope everybody has an excellent afternoon, an evening, depending where you are in the United States. And I look forward to seeing you tomorrow. Have a very good evening. Bye-bye.